So this video is on hemostasis, which is the stopping of bleeding. When there's an injury and a blood vessel is disturbed and it's bleeding, hemostasis takes care of it. It's fast. It's a whole series of reactions that ultimately leads to blood clotting. Now, I'll tell a story of a time that the hose that feeds the washing machine comes out of the wall and goes to the back of the washing machine in our laundry room developed a leak. Water was kind of squirting everywhere. When we discovered it, there's lots of water on the floor. I ran into the laundry room. The first thing I did was I shut off the tap to stop the pressure. Then the next thing I did was I put my thumb over the hole, and then when the pressure decreased a little bit, then I got some duct tape and I duct taped up the hose so that I could finish doing the laundry, and then I replaced the hose because this pressure vessel had developed a leak. So the same thing happens in blood vessels. The very first thing that happens is that you have to reduce the pressure, the blood pressure at the point of the leak. And to do that, what happens is everything before the injury goes into spasm. The walls of the blood vessel go into spasm, and it effectively shuts off the flow to that particular blood vessel. And then after that, platelets form a temporary plug. And then following that, a more effective short-term plug is formed by blood clot. And then after that, it's repaired. But the three stages of the hemostasis, stopping the bleeding, are spasm, platelet plug formation, and blood clotting. So the spasm, which causes vasoconstriction just of the damaged blood vessel, happens because of injury to the blood vessel itself, and then also by chemicals that are released by the endothelial cells that are damaged, and then platelets that are activated. So this constriction keeps on going for quite some time. And it's a lot of that is responsible for the pain you feel when you cut yourselves. The pain reflex also causes spasm itself, so just the feeling of pain. So the point of it is to decrease blood pressure at the site of the injury. So the next thing that happens is that the platelets that are circulating in the blood come into contact with the exposed edges of the connective tissue that supports the endothelium of the blood vessel. So there's a layer below the endothelium that is primarily made up of collagen fibers. And when the endothelium is disturbed, as it is in a cut, then the collagen fibers come into contact with the blood, and that activates platelets. The platelets stick to those collagen fibers with some other proteins, and they swell up, they become spiky and sticky, and then they release chemicals that cause more platelets to activate and stick to the activated platelets and to the edge of the wound, etc., etc. All the while they're releasing chemicals that enhance the vascular spasm. So it becomes positive feedback at this point. The collagen fibers really start the whole ball rolling, but then the platelets, once they're activated, activate more platelets, which activate more, etc., etc., etc. And they end up just filling up the gap of the hole. They act a lot like rice grains in a sink that you've done the dishes. You've washed a rice pot, and the rice is in the dishwater, and as you let the water out of the sink and it goes through the basket, the rice fills up in the basket and basically stops the flow or slows it down considerably. Well, it's the exact same sort of thing. These platelets just block the hole. It ends up looking kind of like this, where the platelets end up filling the hole. Now, step 3 is coagulation, so this is forming a blood clot. And blood gels in this case. So most of you know what a blood clot looks like. I don't have to explain that. It's kind of got the consistency of Jell-O. It really is a gel. There's a little more structure to it, and we're going to see why in a few minutes. But it has that consistency. So what happens is that the platelet plug basically gets reinforced by a protein called fibrin, and then that traps other formed elements, white blood cells, red blood cells, etc., and it ends up just coagulating. Now, there's a couple of phases, and again, this is a nice list of three phases of coagulation. The first step is the formation of something called prothrombin activator. Now, prothrombin is a protein, an enzyme, an inactive enzyme that is circulating in the blood. And when it becomes activated, the prothrombin becomes something called thrombin. Now, thrombin is an active enzyme. When thrombin meets fibrinogen, which is an inactive form of fibrin, it's a globular protein, it causes the fibrinogen to become fibrin, and then the fibrin tangles in itself and sticks to things. It's kind of like silly string at this point. So really, to get the whole ball rolling, we need to make something called prothrombin activator that will make prothrombin turn into thrombin, and the thrombin makes fibrinogen turn into fibrin. Now, it seems like unnecessary steps, except that at each step it's amplified. A very little bit of prothrombin activator activates quite a bit of prothrombin, and that much prothrombin activates an awful lot of fibrinogen. So the steps are for amplification. So how do we make the prothrombin activator? Well, there's two ways that it happens. One's called the intrinsic pathway, and one's called the extrinsic pathway. Now, I'm not going to ask you to memorize these pathways, but here's a diagram of them. These factors are numbered in the Roman numerals in the order that they were found, not in the order that they are used. So 12 becomes 12A, which becomes 11, which becomes 8, which becomes 9, which then becomes 8, and then 10, etc. What I need you to see here is that the intrinsic pathway is really intrinsic to the blood itself. The blood carries the ability to form blood clots intrinsically. Now, that means that blood will clot intrinsically in a test tube or on the floor or any place where the blood is spilt. It doesn't need to be in the body for the intrinsic pathway. But the intrinsic pathway, as you can see, has a whole bunch of steps, and those steps are really quite slow. because of all the factors that have to be involved. There's also an extrinsic pathway, and the extrinsic pathway are factors that are released by the damaged tissue of the blood vessels. So these are called the tissue factors. And you'll see that it's a much more direct line to go from tissue factor to the complex to the prothrombin activator. In reality, most of the time, both of these factors are at work. Both the intrinsic pathway and the extrinsic pathway are happening more or less simultaneously. And again, it's a redundancy, because stopping a bleed is a very important thing. People that have different types of hemophilia have problems with these pathways. They eventually clot, but it takes a little bit longer. So once you get to the prothrombin activator by either pathway or both pathways, then the prothrombin activator turns prothrombin into thrombin. Thrombin makes fibrinogen become fibrin, which then forms a net or a mesh. Okay, this is again talking about the two pathways. Now remember, the intrinsic pathway is just the blood, so it can happen outside the body. Extrinsic pathway is only in the body. It has to be in the damaged tissue. It's a little bit counterintuitive that intrinsic, which normally means within the body, but it means within the blood. Prothrombin activator catalyzes, etc., etc. What you end up getting is something that looks like this. This is a photograph of a fibrin mesh. These things that look like apricots are red blood cells being caught up in this fibrin mesh, and there's a white blood cell there and some platelets here and here, and it ends up forming a network and gives the clot some structure. Now, something that's very interesting is that about half an hour to an hour after the clot is formed, then the platelets themselves have some myosin and actin, the same as muscles have within them. And these activated platelets start to contract, but they're stuck to the collagen fibers, and they're stuck to each other, and they're stuck to the fibrin fibers. And so as they contract and as they basically shrink, they start pulling the edges of the wound closer together, so there's less of a gap to heal, and they squeeze the clot, and the clot becomes a lot less jello-like, and because liquid gets squeezed out of it, so it becomes a little bit denser. So it acts more effectively as a plug, and it also doesn't take as much room in the blood vessel, so it doesn't restrict flow so much. Now, when this is happening, this is when the ache starts to happen. About a half an hour after you've cut yourself, at first it's a stinging sensation in the spasm, and then it turns into this ache, this deep ache, when the clot starts to retract and pulls on the edges of the wound and helps close the wound. Now, any blood that actually gets out and is also clotted in the connective tissue or in any of the surrounding tissue will do the same thing. And so the clot can be quite large, and it basically pulls the wound closed. Now it's time to repair, right? So there's two things that need to be repaired: the smooth muscle walls of the blood vessel and the connective tissue of the blood vessel, so those walls, and then the endothelial lining of the blood vessel needs to be replaced as well. So what ends up happening is there are growth factors released by the platelets that cause smooth muscle cells to undergo mitosis and replace the damaged or missing ones, and fibroblasts to start laying down more collagen and replace the damaged connective tissue. So the walls of the blood vessels start to repair. Now the endothelium around the edges release growth factors that make endothelial cells multiply, and the endothelial lining gets restored. And it works from the outside edges in, so the clot basically is plugging a smaller and smaller hole. But you don't want the clot to come loose and become an embolus. So what happens is, as all of the tissue is repairing, the clot starts to dissolve. It starts to go away, and it usually happens within a couple of days, and it's called fibrinolysis. There's an enzyme that's found within the clot. It's called plasminogen, and plasminogen becomes activated and turns into plasmin by the chemicals that actually form the clot anyways, like so the thrombin and some of the other factors. They activate plasminogen activator, which then makes plasminogen turn into plasmin, and then the fibrin gets digested and removed. So as the tissue heals and the hole gets smaller, the clot is literally dissolving and being taken away. And hopefully it works out that when the tissue is fully healed, the clot is fully gone. A clot that's too big can be dangerous. It can become dislodged and become an embolus, end up in the lungs. It can, or elsewhere, but in veins it usually ends up in the lungs. And if it gets too big, it'll also block the flow in that blood vessel. So you don't want it to get too big. So there are things that limit the size to be just right. So once the leak is plugged, then blood starts just flowing past the clot, and it washes away the clotting factors. So it dilutes it and means that it stops this positive feedback. And then there is an inhibition that the clotting factors start to inhibit themselves once they reach a certain level, and again you end up with the clot growth limited. There are various anticoagulants, like things like heparin, protein C. So they inactivate thrombin. They're just naturally released, and they stop the clot from growing. So you only want this to happen in places where the endothelium of the blood vessel is disrupted. Usually that's by injury, but sometimes endothelium gets disrupted just because of uh, kind of pathologies that damage the endothelium itself. Things like peripheral vascular disease from smoking or diabetes, that kind of thing. Um, so people are prone to forming clots uh, because the endothelium isn't good enough to prevent the clots from forming. Um, there are various other things that are produced: nitric oxide, prostacyclin, that the endothelial cells themselves secrete. Again, so the endothelium, a healthy endothelium, is what keeps it going. Things like vitamin E and quinine also are